So, this is a vertical shading device. Now, vertical shading device has got a horizontal shadow angle. Horizontal shading device something like this at a vertical shadow angle. Vertical shading device has got a horizontal shadow angle. What is this shadow angle? See, this is normal to the this is normal to the window, this is normal to the window, this line and this line is parallel. Sun ray is somewhere here, its projection will be matching this line. This angle we call as horizontal shadow angle, right. So, the angle the tip of the shading device makes it's in horizontal plane touching the window or normal touching the point in the window, which it makes with the normal to the window, that is what it is. So, this angle is nothing but, so if the sun is right now here, then this angle is nothing but the wall solar azimuth, this is nothing but the wall solar azimuth. So, horizontal shadow angle is nothing but wall solar azimuth. So, horizontal shadow angle is nothing but wall solar azimuth, and you can always write it, if this is the length, this is the window width, earlier it was window height, now it is window width, W of window, width of the window. So, this divided by this divided by Ls. So, this divided by W divided by Ls is nothing but 10 delta, which is equals to gamma. Delta is the horizontal shadow angle. So, horizontal shadow angle is given by this. So, at any point of time when you want to block it, that will depend upon this angle will devise, this angle will control that actually, right. So, that is how one can define these angles. If you have an inclined shading device something like this, its effective, you can say, is as good as this, much smaller length, something like a louver, in window, vertical louvers in window, right, instead of something like this. Some places you can close them also, but they will also help you in ventilation. There used to be earlier days, you might have seen that there will be a kind of a all timber piece connecting all of them. You push it up, it becomes horizontal, push it down, completely closes it. So, it can actually, you can make it to move, right, but that length would not be very large. So, but their effectiveness will be, because they will be as good as this much length, they will, because they will block. So, they are as good as this much length, right, this much length. This is shown in horizontal plane, inclined vertical louver it is shown. So, vertical louvers if they are inclined, they actually can block sun's position quite a bit. Egg crate I have already defined, egg crate. So, they will have both vertical shadow angle epsilon and horizontal shadow angle delta, vertical shadow angle epsilon and horizontal shadow angle delta, that is how they are. Now, good old days people would do what? They would use a solar chart. Now, you need not do that, because you can write a small program, calculate out any time, every time, check and do whatever you like. But good old days they would have plotted a solar chart, and these are there in SP 41 or all the books that I have given you in the reference, Kenigsberger's, Marcus and Morris, everywhere you will find this actually. So, this is for 29° north, very close to Delhi. This is very, Delhi is 29 or 29 point something, whatever it is, close to it. So, you can see that what has been done is, you are representing the sky volt in a circular diagram. I mean, you can have, it is a polar coordinate system in a way. So, what you have made? You have made it into plane, the hemisphere made into plane, and these angles are 10°, 20°, 30° and 90° will be somewhere there, 90° will be somewhere there. So, they represent altitude angle. So, you take the projection of the sky volt, right, and the spacings are same, these are called actually equal angle projection, spacing is same, equal angle projection, right. So, this is vertical angles could be like this. Horizontal angle, this is from north, in horizontal azimuthal plane 10, 20, 30, 40 northeast, right, and then east 90 is east, and so on so forth. So, this angles represents azimuth, this angles represents altitude angle. You can have what is called equal angle projection, or some cases called stereographic projection. And if you look at this in equal angle projection, therefore, sun's position in the sky vault is known, because it is known through altitude and azimuth angle. So, you can always find it out, sun's position. So, you can plot, this is for the month of June, this is for the month of June, this is for November, October, November, December, October, and so on so forth. So, each month you can plot. And what about these lines? These lines? No, these are the, see, this is at any point. No, so sun's position, azimuth and altitude angle depends upon what? At a given location, I fix the latitude. So, latitude is fixed, it is a function of the declination, hour angle, declination and hour angle. Latitude is fixed anyway, and declination will change from day to day of the year. That means corresponding to a month I can find out, and hour angle I can find out, corresponding to hour angle and month I can find out. So, this is a month already I have said that this is June, this is October, December, and so on, and this represents 6 am, 7 am, 8 am, 9 am, 10 am, 12 noon, altitude angle of the sun will be at its highest point, right. But it is in summer months, winter months it is much less. So, you can see that it is actually 10, 20, 30, can be as good as 40 degree altitude angle, and the day also is smaller. So, it starts around 7 am to this is 5 pm, this is 6, and so on so forth. So, all of the sun path you can plot it on a chart like this, sun path diagram. Now, supposing I decide that I want to block the sun for certain period of time, then I can just draw it here. I am just saying hypothetically. So, I can actually find out what is the altitude angle of the sun and azimuth angle of the sun which I want to block. Limiting cases, I can find out, and correspondingly I can find out the length of the shading devices. Correspondingly I can find out. So, this is what people were using in good old days. So, equal angle, this is called equal angle projection, but you can have another kind of projection called stereographic projection. In that case, what is done is, this is the nadir, this is the zenith, horizontal plane is here, sun's position is somewhere there. Then this angle 52 degree altitude angle of the sun is represented by a point or circle which will have radius this much. The radius corresponds to sun joining to the nadir, sun point joining to the nadir. So, this is a sphere, celestial sphere, right. So, this point if you join, so it will not be equal. For example, if the sun's position is here, this corresponds to this angle. So, you can see that the spacing will not be same. Earlier 10 degree, 20 degree, 30 degree, etc. they are same. So, they use this. So, you will find that this is 10 degrees more, 20 degrees less, and 70 to 80 degrees still lesser. So, they are not, the angles are, altitude angles are not equal, because it is in curved plane. So, they are trying, you try to project them onto the horizontal plane. So, this is another form of plotting the same thing, and you can plot the same days and hours and all that. So, this is called stereographic projection, but that serves the same purpose. You might find in some book they have shown this, some other books they might have shown this. With the kind of capability, computational capability we have, the diagrams have lost their values. In fact, nobody uses a graph sheet today. Nobody uses, forget about semi-log or log graph paper, you do not even use ordinary log paper today. So, it is all computational. So, you have the formulae, so it is very easy.
During the design, that angle will change, vertical center angle and horizontal side angle.
Yeah, but then you take the extremity, because length has to be the maximum but feasible. If it comes 3 meters overhang, you may not be able to do it. So, there are issues, we will look at that right now. So, basically you take the extremities, extreme cases. So, you see this is the shadow angle. In fact, one could plot them on those graphs as well, they would look something like this. Now, when you want to find out, there are various ways of finding out. Let me see if I have something more to say about this. I will come back to this. Yeah, I will come back to this. I think I will just tell you about this. Now, what you can do is there are various ways of finding out what is the extreme point. One we call it overheated period. For example, I can find out, let us say, tropical summer index values outside. I can find out in shade. I can find out tropical summer index values at shade, because I know the temperature, I know the relative humidity, and do not take the mean radiant temperature, take the dry bulb temperature itself in shade, as if you are not outside, if you are inside, and then cross TSI values you can find out. Now, for TSI value during the daytime I can find out, In other words, I might make it a tabular case, like for summer months, right, say representative days in, let us say I can start from March, April, May, June, etc., and this is, let us say, 6 a.m., 7 a.m. to 8 p.m., 6 a.m., etc., I can find out, because up to 6 p.m. let us say, or 7 p.m., 6 p.m., because I am trying to block the solar radiation. So, during the daytime is good enough, and the TSI values I can find out for each one of these cases, TSI value I can find out. And I know the TSI crossing below, crossing above 30 or 34, I would like to provide shading. Therefore, I can find out the time during which I need the shading, right. I can find out the zone in which I need the shading. So, this is overheated period. This is one way of finding out. Choosing what kind of shading, how much do I want to provide, right. So, the moment outside temperature is increasing, I might like to provide. This is called summer overheated period. Similarly, in winter I would like to bring in the solar radiation as much as possible. So, I might do it for winter months and find out underheated period, where I would like to bring in the, right. Detailed exercise can be done, but then today supposing I want to design, I will tell you in the next class maybe. If you want to design, I can use my computational capability today, rather than just doing by hand and one by one after one variable. So far I have been talking about that how to get the best shape, best orientation, one at a time. And we talked about that in case of hot dry desert climate, you might vary the thermal capacity, or time lag you can find it out, because it depends upon rho L C. So, you can actually massivity of the wall you can find out. So, you can actually find, one by one you can do, but the best way is to put them together and design it. Today we have all sorts of robust computation method through which you can find out, right. Okay, we will come to that. So, coming to simply this, so these are overheated period, and similarly I can find out what is called underheated period. Then I must provide shading device length such that it should actually bring in as much as energy possible during winter, during the underheated period, but minimize the gain during overheated period, right. Other way of determining overheated period is also trying to look at the inside temperature, calculate the inside temperature without assuming any shading device, right. Mean and fluctuating temperature, if you know all other parameters, ventilation, I mean air changes and all that. We have gone through the such procedure, and then inside TSI you can actually obtain.
Shading devices are fixed.
Yeah, they will be fixed. They are fixed actually. They are passive. They are passive. That's right.
So then it's better to have curtains.
No, you can have both. You can have, but then it depends upon human being. Curtains, like blinds and such things, it would depend upon. They have their both. I mean, one is not an alternative to other. You can use both of them even together. So as it has got other purpose also. Shading device, shading or horizontal shading or louvers, if you use, you might even direct the wind direction, change the natural ventilation pattern. So they have multiple uses, but they are also one of them. You cannot just discard them out one for the other. They are not, you can use both of them in unison, one or the other. Decision making is yours. They are good things. So what good about them? That's what we are trying to discuss. So they have multiple use. We are trying to understand what is the use, whether to use them or not is a question. But this doesn't add to extra cost, not too much extra cost, because their sizes are not large, while many other passive system might add to your initial cost high. So cost benefit has to be seen. So coming back to this, how do we design? So we have said that overheated. So then you can define certain efficiency factor. If you can find out overheated period and underheated period, overheated period also you can find out by estimating the temperature without any shading device, which you have done earlier. Put the relative humidity together with it and assume air velocity is 0. Anyway air velocity will only act positively. You can find out the temperature within instead of finding outside, but then you got to know the building itself. And find out during which time you would need shading, overheated period and underheated period, right. So two ways you can do. You can look into the outside in shade, or if you have already a plan, then you can find it out. But then plan, like you have to first you have a decision with the plan itself, then you can find out internal temperature, find out overheated period. Then certain things are defined. For example, this is called we can define some efficiency factor, because I'd like to allow radiation to come in winter, underheated period, but would like to reject the radiation in overheated period. So let us say HO is the heat rejected or blocked during summer, and to the amount of heat incident, total heat incident. Yeah. Today there are so much of actually automated system available with the electronics and instrumentation coming in, varieties of things can be done. So there is possibility, but these are only passive things. Some of them can be straightaway. For example, in an intelligent building, many things just it senses. You have sensors, right? So sensors will sense whether you have come in. Infrared sensing can be there, whether somebody has come in or not. Lights gets on. It also, you can have all varieties of sensors possible. Similarly, you can have sensors which will possibly measure temperature and relative humidity inside, and instead of 2-point often control switch, you can have integral control and all that. So that's or such control, much advanced control system, which will allow the system to operate on its own, but it has to sense even whether it is occupied or not. That's most important, and it's possible. It's all possible with varieties of instrumentation available today. They involve cost, they involve maintenance cost. In large building, it is possible. It's large building, it's possible. It's possible to have all that. But first we must understand the physics behind the basic things. So that's what we are trying to do it in this course. So coming back to this is how we define. This is the ratio of amount of SP is defined like this, and H is the ratio of amount of heat blocked in summer minus amount of heat blocked in winter to amount of heat incident. So this is the total amount of heat incidence on the surface over the year. This is the amount we reject during summer. We are blocking, because if you have a shading device, it will block, and but at the same time it will block some winter heat coming in also. So, net if you look at it, then we define it as He, right. Net if you have, then we define it as He. So, summer shading performance is a set of the shading device. So, this we call as summer shading performance. SP is the summer shading performance. So, performance of shading device during overheated period, that is what we are doing. So, it is the ratio of amount of heat rejected during summer divided by total heat that comes in, that we call it summer shading performance, summer shading performance. And this H is yearly heat efficiency, H is yearly heat efficiency, which is the summer heat coming in minus the winter heat that is did not come in, winter good required heat that did not come in, divided by the total heat came in. So, this we call H is a yearly heat efficiency, and HU is the energy lost during shading during underheated period. So, this is the HU part. So, HO minus HU, this is the underheated which is lost. So, divided by HT, that is algebraically it is like this, HO by HT, HO minus HU divided by HT, right. And then shading effect ratio is defined like this, shading effect ratio is defined like this. What we do is, we have HO, the heat, summer heat which was coming in, minus HU by 2. Why? Because there is a weightage factor, summer cooling is costlier than winter heating. So, that is what we are doing. So, this is the half of this is just given a weightage factor of half, and that is what we are calling it shading effect ratio. So, basically this is the yearly heat efficiency plus the SP, that is summer performance, summer shading performance. So, SP plus HE by 2. So, this half is the weightage factor we are using here, because we assume that cooling is costlier, cooling is more important to us, losing some heat in winter is half, So, putting a weightage factor, and this you can break it up, HO minus HU by 2. So, HO minus HU by 2, you must add, half of this is there. So, there is a just doing the same algebra, you can write it as SP plus HE divided by 2, SP plus HE divided by 2. So, actually you can actually determine the horizontal shading device, length of the horizontal shading device using this kind of concepts. But shading efficiency, if I plot it, this is shading efficiency, AC is the shading effect ratio. If I plot it, shading effect ratio, if I plot it, you will find that as you go on increasing the length, SP obviously, as you increase the length, this is the length actually, this is the length, and this efficiency as a percentage, is as I mean it is actually this is this side, as you is one side is the length. So, as you change the length, SP is HO divided by HT, SP is HO divided by overheated period divided by HT. So, it will go on increasing as I increase the length, as I increase the length along this direction, it will go on improving, right, it will go on improving. What about HE, whatever HE, HE is this line, as I go on increasing, this will tend to reduce it down, because I will block the winter. Up to this point, winter sun does not get touched at all, beyond this it will start blocking, and then combination would be somewhere in between. So, basically there is an optimal length you can find out, which will be governed by this equation actually, best. So, optimal length you can find out, it will be a function of length, SP and HE will be all function of length. So, you can find out a length where this is maximum, you can find out a length where it is maximum. So, that is what you can do, find out a length where half SP plus HE is maximum. So, that is what you know. So, this is how we can do. Now, we can look into another feature, surface texture and color. So far we looked into shading, We looked into orientation, we looked into shape, we looked into construction, U values, and we talked about time lag, etc., etc. Another feature is surface texture and color, alpha. Now, alpha is to short wave should be as low as possible, we have seen, because it is I alpha divided by. So, I do not want this to be too high, right. But also when we try to find out the solar temperature, remember we said that alpha short wave I minus epsilon long wave, right, but this I is not very large actually. So, this should be long wave should be as high as possible. For white color, alpha short wave is 0.4 and epsilon is 0.9, therefore, it is very good, right. So, this is important, surface text color is important, its alpha should be as low as possible, epsilon to long wave should be as high as possible, and whitewash does a very good job. Whitewash does a very good job to that extent, because it has got alpha short wave is around 0.4, epsilon is 0.9, while red brick color would be alpha is high, epsilon is similar, alpha is pretty high, alpha is relatively higher, and if it is blackened surface, that would be pretty bad, in fact, it will have large higher alpha also. So, one can select them, choose them. Then texture is important. Supposing you do rough texture, some sort of texturing, stone protruding out. So, surface area through which heat can be rejected is higher, but mutually some texturing would block the radiation being received on some other parts of the surface. So, intense shading due to projections, that is less absorption, but surface area is increased, more emission. So, we will see if I have some diagram related to that, then earth sheltered I will come later on. So, before we look into the texture for some time, we will look into something called external shading multiplier for. So, basically this we have looked into, that shading of the window is very important. Through projection over the windows, we can actually control the both reduce down the summer heat gain and allow winter heat gain, etc., etc. And vertical fins also can do the same. So, we define something called external shading multipliers to take care of this, what is happening all during throughout the year, or throughout the year. We looked into some of those efficiencies. We will come back to texture again after this. So, we define something called external shading multipliers, right. External shading multipliers. We define something called external shading multiplier is the ratio of total solar gain received through the window shaded by external shading device to that received from the same window if it was completely unshaded. That is what we looked into earlier, HO. We call it something like HO in case of summer. And if I take the total HO plus U underheated period, that is what will be this. So, how do we calculate this out? This is what we like to look into. So, total solar gain through the window shaded by an external shading device is obtained as a sum of total solar radiation on exposed surface and also diffused radiation received on shaded surface multiplied by their respective area. So, total energy gain we would like to look into. So, this beta is solar altitude angle, wall solar azimuth as we have used, and instead of we are trying to use our own notation. This is solar altitude angle normal to the surface, this is wall solar azimuth, and from the north I am defining the azimuth phi or gamma, this is gamma and this phi. So, we will look into this vertical shadow angle already we have calculated. We will make use of some of these and then find out how to calculate out this HO and HH, that is what we will define. Then we will go look into some of those passive features including some issues related to texture and many other passive features in the next class. I think that is what we will do.